Hello students, today we will discuss trajectory and force acting on a moving charge inside electric and magnetic field. First off, we will discuss moving charge inside electric field. Here we have two plates with potential VA, which is positive and represented by blue plate, and the another plate is red plate having potential VB and it is negatively charged. The potential difference between these two plates, delta V, will be VA minus VB. And this potential difference is generally represented by V. Because of these charged plate, they will produce electric field between the plates. And from Gauss law, we know electric field between the two plates having same charge density sigma is equal to sigma by epsilon naught. And the electric field is from positive plate to negative plate. Now, because of this potential difference, the electric field is represented by the equation of line integration. The line integration of electric field intensity is equal to negative of potential difference. For numerical purpose, this equation may be represented as electric field intensity into distance between the two plates is equal to the potential difference between the plates, or the electric field is equal to V by D, volt per meter. Because of this electric field, the charge inside the plate. Now here we have a positive charge represented by blue circle. If it is Q, then it will get a force because of the electric field. The force on the charge Q will be Q into E. As we know, F is equal to Q into E. The force acting on this charge is parallel to the electric field. For positive charge, the force will be directed in the direction of electric field. And for negative charge, look inside the picture. The force is just opposite to the electric field. So the force acting to the moving charge parallel to the electric field is in the direction of electric field or in opposite direction of electric field according to the nature of charge. Hence, the charge will get acceleration. We know force is equal to mass into acceleration. So m into a is equal to q into e, or acceleration is equal to q by m into e. Hence, when moving charge enter parallel to the electric field, it will accelerate it by QE by M. Now in second figure, in figure number 2, the positive charge represented by blue line, blue circle, and this is entering with velocity some perpendicular to the electric field. Then the motion of the charge will be just as the mass when move inside the gravitational field other than horizontal direction, that was parabolic motion. Similarly here, the charge will get a parabolic motion. And if the charge is negative q, represented by red circle, then this moving charge inside the magnetic field perpendicular to them will also get the parabolic path. So when charge moves other than the direction of electric field, it will get a parabolic path or parabolic trajectory. Now in next condition, when moving charge is inside the magnetic field, the moving charge when moves inside the electric field, it also observes a force. The Dutch physicist Hendrik Antoon Lorentz observed that the charged particle moving with velocity v inside the magnetic field B experience a force. So a charged particle also experiences a force inside the magnetic field, and that force is called Lorentz magnetic force. This Lorentz magnetic force depends on number one, the amount of charge. So force is directly proportional to charge. And this Lorentz force also depends on the amount of magnetic field. More the magnetic field, more the amount of force. At the same time, it also depends on velocity component. In this figure, the velocity of charged particle is represented by v. It has two components, v sine theta and v cos theta. Then according to Lorentz, the force acting on moving charge is directly proportional to the component of velocity perpendicular to magnetic field. The component perpendicular to the magnetic field is v sine theta, this one. So, according to Lorentz force, the Lorentz magnetic force depend on charge, depend on component of velocity perpendicular to electric magnetic field, and the amount of magnetic field. So combining these three equations, we will have the equation F is directly proportional to Q V B sine theta. The Lorentz force inside magnetic field on the moving charge F is equal to Q V B sine theta. Here proportionality constant is taken as 1. So we will use this equation for Lorentz force. F is equal to Q V B sine theta. As force is a vector quantity, so it will have that direction also. So to represent the direction, the F is equal to Q V cross B. V cross B will be VB sine theta. And eta is the vector which is perpendicular to velocity and the magnetic field. So force is perpendicular to the velocity as well as force is perpendicular to the magnetic field. Here is a figure representing the direction. If we take a charged particle q here and velocity is tangential, it means the charged particle is moving in a circle. The amount of force will be perpendicular to velocity and the magnetic field. The magnetic field is represented by the cross sign. That is, the magnetic field is perpendicular to the plane and inward. So cross magnetic field means the magnetic field is perpendicular to the plane and inward. Hence, the Lorentz force F is perpendicular to the motion of the charged particle as well as perpendicular to the magnetic field. The direction of force may be also represented by right hand palm rule. Here is right hand palm. The thumb is representing the direction of motion of the charge. Here it is represented by blue line, blue arrow. So this is motion of the charge, that is velocity direction. And the finger are representing the direction of magnetic field. The arrow is represented by red. This is the direction of magnetic field B. The Lorentz force will be represented by the direction of palm, and the direction of palm is represented by the green arrow, and this is the Lorentz force acting on the charge which is moving inside the magnetic field. So we may use the palm rule to find out the direction of force, as well as we have another rule that is called Fleming's left hand rule. Here the forefinger represent the direction of magnetic field. And the other finger are representing the direction of motion of charged particle. Then thumb will represent the direction of Lorentz force. So according to Fleming's left hand rule, the forefinger represent magnetic field, the other finger represent the direction of motion of the charged particle, then the thumb will represent the force. If the force acting on the charged particle is inside electric and magnetic field, it means that moving charged particle is inside electric field and magnetic field. Then we have the Lorentz force F is vector F is equal to vector Fe, that is electric force, plus vector Fb, that is the magnetic force. So it is the vector sum of these two forces. Or simply we may write here F is equal to QE. QE is the electric force and QV cross B is the Lorentz magnetic force. So the Lorentz force inside electric field and magnetic field on a moving charge will be represented by F is equal to QE plus QV cross B. This equation we will use in various devices also. Now let us consider a device that is called cathode ray tube. Or simply CRT. In this tube, we have an electron gun. Inside the tube, there is a cathode, which is negatively charged by very large voltage, and the anode, which is positively charged by the large voltage. The cathode may release the electron. These thermal electrons, which are released from the cathode, will move toward the anode because anode is positively charged. Inside this tube, the anodes are grid type, just like as a net. The electrons are accelerated by the electric field between anode and cathode, and they move toward the grid of the anode, that is net of the anode, and because of their high kinetic energy, they come out in form of cathode ray. The beam of electron is called cathode ray. Look on this figure of cathode ray tube. There are two plates which are charged and they will produce electric field. And the two ends of the electromagnet which produce the magnetic field B. So the charged particle is moving inside the two fields which are perpendicular to each other in this cathode ray tube, and the cathode ray, that is beam of electron, will hit the fluorescent screen of the cathode ray and give a point which tells the position of the electron beam. The complete arrangement is cathode ray tube, and the experiment in which we will find the charge to mass ratio is called Thomson experiment. Inside the Thomson experiment, we will find charge to mass ratio of electron. Initially, two fields are used simultaneously, the electric field by the charged plate and the magnetic field by the electromagnet. They are perpendicular to each other. Now, the charge, that is electron beam, is coming inside this electric and magnetic field. As we know, E is equal to V by D, so we may control the amount of electric field by controlling the potential difference between the plates. So we may adjust the voltage to get the proper amount of electric field. And we also know for a solenoid, the magnetic field is equal to mu 0 Ni. N was number of turn per unit length and I is the current. So we manage the amount of magnetic field by controlling the current. So by controlling the voltage between the plates, we manage the amount of electron what we need, and by controlling the current we will get the proper amount of magnetic field by the electromagnet. So in first case, we adjust the voltage and current in such a way the net magnetic force and electric force neutralize the effect of each other. That is, net Lorentz force became zero. So at this condition, the magnitude of electric field will be equal to magnitude of magnetic field. The beam of the electron will strike on the fluorescent screen without any deflection. In this condition, that because the Lorentz force became zero. The electric force will be E into E, because we know electric force is Q into E. Q is charge, and in place of here charge is E, and is equal to QVB. So it will be EVB, or what we will get? We will get V is equal to E by B. This equation is also known as velocity selector equation. The charged particle moves undeviated when E by B is equal to V. So by this method, we will get the velocity of charged particles. Because we know electric field, as we know B, that is magnetic field because we know I. So we will able to get the velocity of the charged particle, that is electron. In second part of the experiment, we change the value of E as 0. That is, there is no electric field. If there is no electric field, it means there will be no electric force on the electron. So there will be only a magnetic field. As we know, the magnetic field is perpendicular to the velocity and also perpendicular to the magnetic field. So Lorentz magnetic force is perpendicular to the motion of the charged particle, will give the centripetal force. Hence, the centripetal force will be the magnetic force acting on this electron. Because of the centripetal force, the charged particle will take a circular path and will hit at the ends of the fluorescent stream, and we will able to get the radius. The centripetal force on the charged electron is equal to mv square upon r, and it will be equal to qvb. mv upon r will be equal to E into B. E is charge of electron. V and square cancel each other. Same time we know the value of V from velocity selector equation. V was equal to E by B, and it is equal to EB, or E by M is equal to capital E upon R B square. From this equation, we will able to find out the charge to mass ratio of electron, because we know value of E, we know value of B, we know value of R from this cathode ray tube. So by Thomson experiment, we will able to get charge to mass ratio. So this was the one of the application of Lorentz force inside electric field and magnetic field. Thank you for watching the video.